Borescope reading on auxiliary hydraulic line is stable.
Confirmed. Data matches expected parameters.
Aspirants. Inside this clean and disciplined environment, one question always appears in the minds of people entering aviation for the first time.
When people look at the parallel electrical lines inside the technical compartment, or the multiple layers of control units stacked together, in aviation, the most dangerous thing is not the appearance of a failure, but the moment there are no remaining options once that failure happens in the sky.
The narrow-body aircraft rests inside the maintenance hangar like a giant living organism, having every vein inspected before returning to the pressure and uncertainty of the sky. A technical schematic showing that nearly every critical aircraft system exists in multiple silent backup layers that passengers never see.
At that moment, the central question of the video slowly emerges beneath the sound of ventilation fans and the reflections on the matte gray metal. Why does an aircraft need so many?
People who have never worked in aviation often believe modern technology is advanced enough to create systems that never fail. But aviation itself is built on the exact opposite belief.
In the world of flights cruising tens of thousands of feet above the ground, every engineer must accept that any component can eventually fail at a moment nobody expects.
That is why the entire aviation industry is not built around the idea of preventing every failure from happening, but around the ability to continue.
Under normal operating conditions, the narrow-body aircraft, with its matte gray metallic body and no logos or markings,
A modern aircraft needs electricity to operate flight systems, hydraulics to control flight surfaces, computers to calculate.
If everything works perfectly, passengers almost never realize that behind every smooth flight, thousands of components are operating simultaneously under continuous pressure.
Inside the technical compartment, beneath the aircraft floor, electrical lines are divided into independent branches so that if one branch fails, the remaining branch can continue on.
The female Caucasian engineer between 22 and 25 points toward the flight control unit and explains that even the most critical computers often exist as multiple processors.
That is why engineers do not only ask how well a system performs, but also what will happen if one part of that system suddenly disappears during flight.
In every inspection inside the maintenance hangar, the focus is not only on operational efficiency, but also on the aircraft.
The contradiction begins to appear when people realize that the more backup systems are added, the heavier the aircraft becomes.
Every additional kilogram directly affects fuel usage and operational efficiency. If viewed only from a simple economic perspective, removing some backup systems would seem to save airlines enormous operational costs over many years.
But aviation is not an industry allowed to ask how to become cheaper, before asking how to survive when a failure happens in the sky.
Losing even one control system at the worst possible moment can completely alter the aircraft's stability within only a few seconds.
The terrifying part is not the technical failure itself, but the moment the pilots no longer have another system available to continue controlling the aircraft after that failure occurs.
Inside the clean and quiet maintenance hangar behind the terminal, workers between 22 and 25 inspect every.
Modern aircraft are not designed around the belief that everything must remain perfect forever, but around the belief that everything can eventually fail.
The deeper people look into the systems inside an aircraft, the more they realize that redundancy is not an added feature.
When passengers feel calm inside the cabin, what they are truly trusting is not absolute perfection, but the aircraft's ability to still have another option available.
The core reason backup systems become so important begins with a simple truth that aircraft operate in an environment. Unlike a car that can stop during a malfunction, the narrow-body aircraft with matte gray metallic surface and no logos must remain stable at high altitude. Every aviation design must answer one question. What happens if the primary system stops functioning during a flight lasting hours above oceans or mountains?
That is why redundancy is not simply about copying another identical component, but about creating the ability the aircraft.
In many situations, backup systems are designed separately from the primary systems to prevent one single failure from destroying the.
Even the installation position must be calculated carefully to avoid one failure damaging multiple systems simultaneously.
The aviation industry clearly understands that accidents rarely come from a single failure, but from the moment multiple layers. That is why a modern aircraft may carry multiple electrical sources, multiple flight control computers, multiple hydraulic pumps. Inside the maintenance hangar behind the terminal, workers continuously perform cross-check inspections between primary and secondary.
In aviation, backup systems are not created because of pessimism, but because humans clearly understand the limits of machines.
The more advanced aircraft become, the more layers of redundancy they require, because as technology grows more complex, the consequence sports. The greatest difference between aviation and many other industries is that aviation always assumes the failure will happen at the worst possible moment.
No matter how advanced a single system may be, it still carries the probability of failure. Multiple coordinated backup systems.
From the outside, backup systems may seem to make aircraft heavier and more complicated, but from the perspective of safety, they are the very reason.
Forge meets. Inside the quiet maintenance hangar behind the terminal, workers between 22 and 25 replace components regularly even while they still function.
Historical maintenance records showing that many serious incidents in the past were successfully controlled only because of backup systems that passengers never even realized existed.
This creates a fascinating paradox that the more effectively redundancy systems work, the less passengers realize they exist.
In many industries, people try to simplify everything in order to reduce costs. Extreme simplification can sometimes become the greatest danger of all.
Redundancy is not a sign of distrust in technology, but a sign of maturity in engineering thinking.
Workers between 22 and 25 continue inspecting every small sensor inside the clean and disciplined maintenance hangar. Police. When people look back at the modern aviation industry, they begin to understand that redundancy is not only a technical solution.
Aircraft fly safely not because humans believe failure will never happen, but because they prepare a second path before failure appears for the very first time. Inside the quiet space behind the terminal, the most important philosophy of aviation gradually becomes clear.
Backup systems become important because the sky does not allow humans a second chance to correct mistakes once every final option has disappeared.
And that is also why modern aircraft carry so many silent layers of protection, because in aviation, survival always begins with
In the world of modern aviation, what truly gives people confidence is not the promise that failure will never appear. And from that, people understand that redundancy in aircraft is not only a technical method of protecting flights,